We all think we know the story of the ionic bond. You've got a positive ion, a negative ion, and bam, they stick together. Simple, right? But what if I told you that simple attraction is actually hiding a secret power struggle, a hidden drama that determines the real strength of that bond?
And figuring out the drama is the key to answering a really fundamental question. Why can you melt some salts without much fuss, while others need absolutely scorching temperatures? The secret, as we're about to see, is all tangled up in the true nature of the bond itself.
Okay, so let's start with the classic story. The one we all learned from a textbook. It's a very neat, very tidy tale of a simple, perfect attraction.
So the official definition says an ionic bond is just the electrostatic pull between a positive and a negative ion. And this attraction is incredibly strong. That's why most ionic compounds, think about table salt, are totally solid at room temperature. Those particles are locked in tight.
In this perfect little world, like in a crystal of table salt, every single positive sodium ion is perfectly gridlocked, surrounded by 6 negative chloride ions. It's a rigid, strong, super orderly structure. But, well, reality is almost always a little bit messier than that.
To really get that messiness, we need to properly meet the main characters in this little drama, the positive cation and the negative anion.
And listen, these two ions could not be more different. The cation, that's the positive one. Think of it as small, dense, and powerful. Its positive nucleus has this iron grip on its electrons, keeping them in a tight, symmetric cloud. And then you've got the anion. It's large, kind of fluffy, and its outermost electrons are way, way out on the fringe, held pretty loosely. This makes its whole electron cloud soft, almost vulnerable.
So right there, these fundamental differences create a totally unequal power dynamic. It's not just a simple attraction anymore. It becomes an interaction where one ion has a very real influence over the other.
And this is where the cation gets to show off its special ability, something we call polarizing power. Because all of its positive charge is packed into such a tiny space, it can actually reach out and pull on that soft, fluffy electron cloud of the anion, literally distorting its shape.
Now, the anion has its own corresponding trait, polarizability. And this is really just a fancy word for how easy it is for its electron cloud to get distorted. Since its electrons are so loosely held, a big anion is highly polarizable. It's easily influenced.
So what gives a cation this awesome polarizing power? It really comes down to two main things. First, a higher positive charge gives it more pulling power. That makes sense. And second, a smaller size concentrates that charge, making the pull even stronger. When you combine these two ideas, you get the key metric here, charge density. A high charge density means a whole lot of polarizing power.
Okay, so what happens when a powerful cation gets close to a really polarizable anion? Well, the result is that the bond itself gets distorted. We move from that perfect ideal to the much more interesting reality. So in our perfect textbook world, you've got two ions sitting next to each other as these perfect, separate little spheres. The electrons have been fully transferred. We call this a pure ionic bond. This is our before picture. But in the real world, that cation's polarizing power gets to work. It starts tugging on the anion's electron cloud, stretching it out and pulling that electron density into the space between the two ions. The anion is now officially polarized. And this is the after picture, and it changes absolutely everything. And here it is. This is the absolute key to all of this. When that electron cloud gets pulled into the space between the two ions, they aren't just electrostatically attracted anymore. Nope, they've started to share those electrons. And what is sharing electrons? Well, that's the whole definition of a covalent bond. So our supposedly ionic bond isn't so pure anymore. It's picked up some covalent character.
Now, this might seem like a tiny little detail in chemistry, but trust me, it has massive, real-world consequences. It's how we're going to finally answer that question about melting points.
This chain of events basically explains it all. The more polarization you get, the more covalent character the bond has. This sharing actually messes with the perfect separation of charge, and that weakens the pure electrostatic pull of the ionic bond. And a weaker bond? Well, that's easier to break, which means it takes less heat. The end result? A lower melting point. Simple as that.
Let's see this in action. A perfect real-world example is the carbonates from group 2 on the periodic table. Now, for these compounds, breaking the bond makes them decompose instead of melt, but the principle is exactly the same. A stronger bond needs more heat. So as we go down this group on the table, from beryllium to magnesium to calcium, the positive cation gets bigger and bigger with each step.
So, follow the logic here. A larger cation means its positive charge is more spread out, so its polarizing power goes way down. Less polarizing power means less distortion of the anion, and the bond becomes more purely ionic. And a purer, stronger ionic bond needs a lot more heat to break it apart.
And what do you know, the data proves it beautifully. Just look at this chart. It shows the temperature needed to decompose these carbonates. Beryllium carbonate, with its tiny superpolarizing cation, breaks apart at a pretty low temperature. But as you go down the group to magnesium and then to calcium, the temperature needed just keeps climbing. It's exactly what our theory predicts.
So, there you have it. The secret is out. That simple, pure ionic bond we all learned about in the textbook, it's kind of a myth. The reality is that ionic bonds exist on a spectrum, and how much covalent character they have, which is all driven by polarization, is what truly decides their strength and, in the end, their melting point.
It really makes you think, doesn't it? If the simple ionic bond has this much amazing complexity hiding just under the surface, how many other simple rules in science are just the beginning of a much deeper and way more fascinating story?